Hello my dear students, you're welcome to this lesson and to this topic in particular. Our topic today is called dimensional analysis. This is the first topic in A-level physics paper 1 under mechanics. You're all most welcome. We're going to be having a series of lessons, like around 3 lessons in this topic. And by the end of this topic, each one of us must be able to define the term physical quantities and give you examples with the units. Define basic, or what you call the base or fundamental quantities, and give examples with the ends as well. And derive the physical quantities, give examples and the ends. You must be able also to state what is meant by the term dimensions of a physical quantity. And then lastly, you should be able to use the knowledge of dimensional analysis to check for the consistency of equations and then to derive equations as well. You should also give reasons as to why this knowledge of dimensional analysis is not suitable, is not the best, is not okay, is not good in checking for the validity of equations. So that is what you should be able to do by the end of this topic, which is going to be covered in 2 lessons. You are most welcome. So let's begin. Dimensional analysis. What are the terms that we use in this? The terms that we use are basically 3 of them, and I'm going to begin by giving a short exercise. You're going to pause the video and try it out. So the question says that state and give examples of what is meant by a physical quantity, a basic quantity, and a derived physical quantity. Define them, give examples, and then I'm giving you something like 2 minutes. Pause the video and try it. So the first term that we're going to be looking at is a physical quantity, and we define a physical quantity as that measurable quantity that can be expressed in terms of numbers and units. For example, mass, length, time, acceleration, speed, very many of them. So long as you can quantify it, so long as you can measure it and express it in terms of a number and a unit, we call that one a physical quantity. Of course, we have non-physical ones that cannot be quantified. For example, the mood of a person, for example, the love, for example, the beauty of something. All those ones are non-physical. So in physics, we deal with the physical quantities. And among the physical quantities, we have what called the base, or the basic, or the fundamental quantities. All the 3 names mean the same thing, the basic quantities. And then the other one is called a derived physical quantity. So base or fundamental quantities are those quantities that cannot be expressed in terms of other quantities. They cannot be got by either multiplication, division, or any other mathematical expression of other quantities. So those are fundamental quantities, and there are basically 7 of them. We have the mass, length, time, temperature, electric current, luminosity, or light intensity, and then the amount of a substance. And usually express them like this, that the length, the mass m, we give it a small letter m. The name of its SI unit is a kilogram, and we write it as a small k and then the g. So another one is the length, its SI unit is a meter, unit is a small m. The symbol is a small m. We have time, we have electric current, we have temperature interval, and the SI unit of temperature is a capital K, which is a Kelvin. For the electric current, we have the amperes, capital A. And then the amount of substance, we normally use the small letter n to represent that, and its SI unit is a mole. And then luminous intensity, what we call the light intensity, the symbol is capital I, and its SI unit is a candela, CD, small letter. So those are the 7 base quantities. Now, in this lesson of dimensional analysis, we shall be paying more attention to these 3: mass, length, and time. Derived physical quantities. What are these? Sometimes we call these ones the dimensional quantities. And these are quantities that can be expressed in terms of the base quantities. In other words, they are got from the fundamental quantities. You can either use multiplication, division, and get these ones here. So they include, for example, area, volume, density, pressure, force, momentum, acceleration, speed, velocity, and very many others. So long as you can get these ones, so long as you can see that these ones are got from the fundamental quantities, either by division or multiplication, we call those ones the derived physical quantities. And likewise, we have these units here. For area, the SI unit is a meter squared. For volume, meters cubed. You know all of these from your O-level physics. One thing that I need to notify you about the units is that we have some special derived physical quantities whose units normally begin with a capital letter. For example, we have force. Its SI unit is a capital N, and when writing it as a word, we use the letter small n. The reason for this is that we simply remember the great scientists, the great philosophers who came up with these quantities, or who used to simplify these quantities here. So Newton, remember the name Sir Isaac Newton. Likewise, the SI unit of work and energy is a joule, capital J, and you can express this in terms of the base units as this. We shall see this later on. Then a watt, pascals, coulomb, a voltage, an ohm, and then a Hertz. All these ones are SI units of these derived physical quantities. So after having looked at all these units here, all these fundamental and derived physical quantities, let's now go to dimensions of a physical quantity. What is the meaning of the word dimensions? What does it mean? So we define dimensions of a physical quantity as a way of expressing all the derived physical quantities in terms of the base quantities, in terms of the fundamental quantities of length, mass, and time. So for example, in case I talk of area, of force, of work, if you can express all of those in terms of the base quantities of mass, length, and time, then whatever you've got is what you call the dimensions of a physical quantity. And the symbol for dimensions of physical quantity is this kind of bracket here, not any other bracket. For example, this one, whenever I see something like this is read as the dimensions of force, dimensions of area, dimensions of pressure, and very many others. Now, to begin with, for the mass, length, and time, the dimensions of mass is a capital M. Remember, we can represent M as the mass of a substance, small m. To distinguish that one from dimensions, always give the mass capital M. Dimensions of length likewise is given a capital L, and dimensions of time is given as a capital T. These are dimensions of the fundamental quantities of mass, length, and time. Now, for other derived quantities, in case we want to express them in terms of the mass, length, and time, it is always better that you try to remember, try to recall the equation of getting that quantity there. For example, area is got from length times width. And remember that length is the same as width, not that they're all distances. So it is length times length. So what we shall do is that instead of simply having this, we shall simply have dimensions of area is equal to dimensions of length times dimensions of length. As simple as that. In other words, dimension of area is equal to dimension of length times the dimension of length. And this is the same as capital L times capital L, which gives us L squared. Now, if you remove this symbol for dimensions, then you simply write the capital L, the capital M, the capital T, where they are needed. So that is what we do have. Try out for the velocity and the volume. Try to get these dimensions of velocity and for the volume. Pause the video. Okay, so velocity is the same as speed. It is the same as speed, on that velocity is vector, speed is scalar, but they all have the same dimensions. And remember that speed is equal to distance out of the time. So the dimension of speed, that's now introducing the symbol. Dimension of speed is equal to dimension of distance over the dimension of time. And this is the same for distance, that is length, capital L, divided by dimension of time, which is capital T. And in the scientific form, this is the same as capital L T to the power of -1. In other words, there is a power 1 here. When I move this division symbol, it becomes a -1. So this is the dimension of speed or of velocity. In case you got this, that is wonderful. Likewise, volume is got from length times width times the height. So this is the same as dimensions of length times the dimensions of width times the dimensions of the height. But at the back of your mind, just know that for the length, the dimension is capital L. For the width, that is still length, the dimension is capital L. And for the height, that is also length, the dimension is capital L. And therefore, the dimension of volume is simply capital L cubed. Now, if you look closely, you can tell that where you have L, length, do you recall the SI unit of length? That is a meter, yes. So, it means that the unit of area is a meter squared. For the velocity or for the speed, it is L divided by T. So the unit is meters per second. And then for volume, it is meters cubed. So you can note that there is a relationship between the dimensions and the units. We shall talk more about this in the next part. Another example is there. Still, you can pause the video and try out all of these. The choice is yours. Okay, so let's begin. Acceleration. Acceleration is got from the change in velocity over the change in the time, which means therefore that the dimension of acceleration is the same as the dimensions of the velocity divided by the dimension of the time. And the dimension of velocity, we got it as Lt power negative 1. In other words, remember, meters per second. So it is length time power negative 1. Then divided by the dimension of time is a capital T power 1. So we take this one to the numerator, we'll get the final dimension of the acceleration as Lt power negative 2. And that is the dimension of acceleration. For the force, this is the same as, remember that force is equal to ma. So meaning that the dimension of force is the same as dimension of mass times the dimension of acceleration. And this, for mass, it is capital M. For acceleration, it is Lt power negative 2. And this is the dimension. Work done. What is work? Work done is the same as force times the distance moved in the direction of the force. Force times distance. So meaning therefore that the dimension of work done is the same as the dimension of the force times the dimension of the distance. You can split these ones. I'm just introducing in this just to show that it is also possible. So it is the same as the dimension of the force times the dimension of the distance. And the dimension of the force, we've got it as ml t power negative 2. And the dimension of the distance, which is length, is simply capital L. Therefore, the dimension of work done is equal to m. We have 1 here, we have 1 there. So L times L, we get L squared. So we have ml squared t power negative 2 as the dimension of the work done. Likewise, power. What is power? Power is equal to work done out of the time taken. So the dimension of power, therefore, is the same as dimension of work done divided by dimension of time, which is the same as ml squared t power negative 2 divided by capital T, and this will give us ml squared. There's a 1 here, so when it goes up, it will be minus 2 minus 1. Remember indices in math. So t power negative 3 as the dimension of power. So you have this exercise as well. You can try it out very fast. And remember that impulse is the same as force times time. Or simply impulse is the same as the change in momentum. Change in momentum. Momentum is mass times velocity. Okay, so energy is the same as work done. So its dimension is the same as ml squared t power negative 2. Pressure is force over area, ml power negative 1 t power negative 2. Momentum is mass times velocity, so we have ml t power negative 1. And then impulse is force times time, which is the same as ml t power negative 1 as the answer. So In all of them, remember that when writing your answer, don't forget the unit, I mean the symbol for dimension. In case you forget it, then it will be wrong. For example, you simply say that energy, dimension of energy is equal to ml squared t power negative 2. That is how you state your answer. This knowledge of the dimensions of a physical quantity is applied in two ways. One, in deriving equations. For example, the equation of work done is equal to force times distance. Where does this equation come from? How do you derive it? So that is using the knowledge of dimensional analysis. And then two, we can also use this knowledge of dimensional analysis in checking for the consistency of equations. I will explain what that means, consistency of equations. Now we also need to note that this knowledge of dimensions is not used in checking for the validity, in checking for the correctness of an equation. For example, you can have an equation of V is equal to 2U plus 10AT. This equation is dimensionally consistent, we shall see this later on, but this equation is wrong. The correct equation is supposed to be V is equal to U plus AT. In other words, the first equation of motion. So, the knowledge of dimensions can check for the consistency of equations, but it cannot check for the validity of or the correctness of an equation. So in the next part, we shall be looking at checking for the consistency of equations. I'm stopping here for now. See you.